Hello, and welcome back to CS 500 Design and Analysis of Algorithms. In Chapter 4, we're going to motivate amortized analysis with our example of the increment of a binary counter, which we already discussed in the case of average case analysis. But now we're going to take it from the perspective of amortized analysis, and then we're going to generalize that from repeatedly incrementing to repeatedly adding binary powers of 2, which will turn out to be interesting application later when we talk about Fibonacci heaps and analyzing this data structure. We're going to compare what is the similarities and differences between amortized analysis on the one hand and average case analysis on the other hand, as opposed to our traditional paradigm of worst case analysis. Then we'll proceed to the already mentioned Fibonacci heaps, a new data structure that allows to realize priority queue with drastically improved amortized costs. The worst case cost is actually worse than, for example, binomial heaps, but the amortized cost is better. Almost every operation has constant amortized cost, and this data structure is comprised from relaxed binomial trees. So where binomial heaps are a collection of binomial trees, Fibonacci heaps are a collection of relaxed binomial trees. Then we're going to recall the operations supported by Fibonacci heaps, and particular emphasis on the interesting new ways of realizing the extract min operation and the decrease key operation, so that in particular the decrease key operation turns out to have constant amortized cost, and the extract min operation is the only one that has super constant amortized cost, namely logarithmic amortized cost. Then we talk about applications of this priority queue realization based on Fibonacci heaps, namely applications when computing minimum spanning trees in previous algorithm, which we had analyzed before with binomial heaps, and now we're going to analyze it again building on Fibonacci heaps. Another famous algorithm for computing minimum spanning trees is Kruskal's algorithm. And here we're going to introduce the union find data type, which is a data type that Kruskal's algorithm builds upon. And then we're going to discuss different ways of realizing this union find or disjoint set data type, namely with a very slow but non-constant amortized cost. And in order to formalize what that means, we're going to talk about fast-growing functions, polynomial, exponential, doubly exponential, triple, and even more faster-growing functions on the one side, and on the other side, slowly growing functions, namely the inverses of these fast-growing functions. Then we're going to discuss the first way of realizing such a disjoint set data structure, namely using the union by weight heuristic. And we're going to analyze that heuristic and thus turn it into an actual algorithm. And finally, we're going to discuss another way of realizing a disjoint set data structure, namely using the lazy union by rank heuristics with path compression. And again, we're going to analyze that heuristic and thus turn it into a proper algorithm. So that's an overall overview for Chapter 4, but today we're by far not going to be able to cover everything. So let's start slowly by recalling the motivation, namely the binary bit cost of repeatedly incrementing. So recall our binary counter, and in the case of average case, we would charge the cost, the number of bits that flip when incrementing that counter. And in the average case, we would consider this counter starting with an average number, starting with some arbitrary average number. We take the average over any possible starting number and then increment it once. That was average case analysis. Now, in amortized case, we take a different perspective. Namely, we start the counter with 0, but we increment it repeatedly several times. So that's a subtle but important difference. In average case analysis, we start with a typical value and then invoke the operation once, in this case, the increment operation. In amortized analysis, we start with the initial value 0 and then apply the operation repeatedly. In both cases, we take then the average. In the first case, the average over the initial value at one increment. In the current case, we take the average over the cost of repeated increment. So to remind you, now we start with counter value 0 and we increment repeatedly. And we've already analyzed kind of the cost of a typical increment, and mathematically both amount to the same quantity, but their meaning is now a different one. So in the worst case, one increment has of value up to n can have almost all bits flip. And how many bits are there in a count of value up to n? There can be at most logarithmic n many bits, and almost all of them can flip in the worst case. Now, when we take that worst case analysis and apply it repeatedly for the case of repeatedly incrementing, that means if we increment the counter m times, and each time can have at most cost log m, then that means that the cost of repeatedly incrementing can be up to m log m. That's worst case analysis applied repeatedly, but this is an overestimation. This worst case does occur, but it is very rare among the many repeated increments. So that's why we now proceed to a more careful analysis. Namely, we count during the repeated increments how often does the first bit, the bit number 0, flip, the least significant bit. And that flips every single time. You see that? The least significant bit flips every single time. So when we increment the counter m times, that means bit number 0 flips m times. Let's now count how often the next significant bit flips. The next significant bit flips every second time only. So here it does not flip, then it flips. No flip, then flip. So how often does the next significant bit, the bit with number 1, flip? It flips only half of the times. That is, among the m increments, it flips m over 2 times. And similarly, the next significant bit, the bit number 2, flips on every 4th time. So in m repeated increments, that means m over 4 times does this bit flip. And not considering all possible bits means we count the number of bit flips, but by kind of rearranging this sum, we realize that the first bit flips m time, the next m over 2 times, next m over 4 times, and this is kind of a geometric series. Well, it's a finite geometric sum, but bounded by the infinite geometric series. So the value of all this sum is at most less than 2 times m. M plus half m plus 1/4 m, and so on. That's 2 times m. So that's constant times m for the entire sequence of m increment operations. And now amortizing that cost 2 times m over the m increment operations means that the amortized cost per single increment operation is 2 bit flips. So that was the first very basic example of amortized analysis and how that gives a more realistic prediction of the actual behavior than repeated worst case analysis. Namely, now the total number of bit flips turns out to be just linear as opposed to m log m. One way of looking at this amortized analysis is by allowing the program to maintain a kind of savings amount. Let me illustrate that. One way to formalize that is to have a savings account and to analyze the balance of that savings account as that changes over time. So initially, the savings account has some value, phi 0, which is maybe let's simply say that this is 0. If we start with an empty savings account, and during the operation of this data type, there's an actual cost of each operation. Let's denote that by Cm. Cm is the cost of the mth increment operation. But we also have the corresponding balance of the savings account that may go up and down over time. And one way of looking at this mathematically is by considering this purely mathematical inequality. So the left-hand side is kind of the amortized cost, namely the overall sum of all the cost of each operation. So we sum all the cost of all operations from small m up to capital M, and then we amortize that bit. That is, we take the average cost of the average operation, we divide by m. That's the left-hand side. And the right-hand side is a purely mathematical estimate, which says that this is at most the maximum cost. And now I'm going to interpret this. This is the cost of the m operation plus the difference in the bank account. So that means we can, in each step, we can either put some money into the bank account, which means that this difference actually becomes positive, right? So putting money in the bank account means that after the mth operation, the bank account value is larger than before. Then before means after the m minus first operation. So the bank account increases, means this difference is positive, plus the actual cost. On the other hand, when the actual cost maybe is large, then we can compensate for that by withdrawing money from the bank account. Withdrawing money from the bank account means this difference becomes negative. After the nth operation, the bank account balance is smaller than before. So smaller minus large means something negative. And so that means we can compensate for large cost, large CM, with something negative to make this number small. And the goal is to have the maximum of this number small, so that in all cases we can charge the same small numbers. Sometimes we use, when the cost is small, we charge more to put into the bank account and thus increase that. In other cases, when the cost is large, then we use the bank account to withdraw money and to reduce the size of this sum, so that in all cases, we want to make that sum as small as possible and therefore the maximum small as possible. And this is kind of the initial and final condition, the initial bank account value, and the bank account must never be negative. So here we subtract something divided by m. So that's the interpretation of this term, so that this is something negative. But again, this is a purely mathematical estimate that I recommend you practice to prove mathematically. So, and the goal is to devise a kind of policy for ourselves for maintaining the bank account. So we design a policy for maintain a savings account in such a way that this quantity becomes small. That's a kind of abstract perspective. In the case of the repeated increment, the policy that works, that recovers this analysis. So now we take a different perspective on this amortized analysis. Now, with the perspective of a savings account, is the policy that we use is that the balance of the savings account after the nth operation should be equal to the number of digit ones in the counter after the nth operation. So this is kind of our own policy that we make up for ourselves. And then we analyze that. So how do we analyze that? Well, we verify that the cost of the increment, which may differ, right, plus the difference between the number of ones after and before the nth operation, this is always equal to 2. Constant. So let me say that again. The number of bits that flip from m to m plus from m minus 1 to mth operation, plus the difference in the number of ones, which, as you recall, is our bank account balance policy. This is always exactly equal to 2. Again, I recommend you to verify that and prove that. And as said before, this is never positive. So that means that this maximum, this is always equal to 2. Therefore, the maximum is also 2. And here's something negative. So this is less or equal to 2. So in this way, we can recover our previous kind of ad hoc analysis of the binary counter now with this general method of maintaining a savings account according to some policy that we design ourselves in such a way that this maximum becomes as small as possible. And the result is the same in both cases. We analyze the amortized cost of repeated increment in 2 different ways. So let me explain you why it's called amortized analysis and how that savings account intuition, where that comes from. And that comes from regular businesses. So here's an example of an advertisement of some repair service. And this is a fixed price repair service. So they charge 144 euros for repairing your, let's say, car, oil and filter, air filter, pollen filter, clean, adjust rear brakes. It's always just $144, regardless of the actual cost, right? So that's why it's called fixed service or flat rate service. Now, a garage running that service may sometimes actually make a loss, right? So for some cars, maybe some very old car comes in and it is much more expensive than $144 to repair that old car. On the other hand, maybe some old broken cars are very rare, and maybe the average car is much cheaper. So in this way, the garage can maintain its service by amortizing the few expensive to be repaired, the few broken cars, amortize for them by in turn charging a little bit more than the actual cost for the majority of the well-maintained cars. So here you see, for example, a car that requires very little for repair, the famous Beetle, right? So whenever such a car enters the garage, maybe they don't need 144 euro, but maybe much less to repair that car. And hopefully that's the majority. On the other hand, when a very broken car enters the garage, maybe they need to put in much more effort and more expensive to repair such a car. but hopefully that's a rare case so that they can amortize that rare case over the common case. That's a business perspective on amortized analysis. And the question is, of course, how cheap can such a garage offer such a service? Maybe there's a competing garage that performs a more close analysis of the types of cars and the cost of cars that come for repair. And maybe a competing garage can offer also a fixed price service, a flat price rate service, charging less than 144 euros. So the question is, what is the cheapest price that one such a garage can offer, and without ever going out of business, that is without running into debt with their savings account? It's a savings account that can accumulate but never go into the negative, never go into the debt. So that's for very mechanical flat rate or fixed price service amortized analysis. And we're here in computer science, so we kind of consider the same for maybe IT flat rate service. Maybe somebody comes with a computer problem and you want to fix it at a fixed price, regardless of what the problem is, regardless of what the computer is. So that's a kind of a motivation or a background of amortized analysis, computer science, originating actually in business, in economics. And so the goal is to kind of devise for yourself, for ourselves, a policy on how to maintain the savings account and then analyze it, right? So imagine this phi m to be the bank balance before the mth operation, where Cm is the cost of the mth operation. So this is difference means the difference in the bank account value. It means how much money you take out of the bank account or how much money you put into the bank account in the mth operation. Okay, so much for the analysis. And just a second here. Yes, and the kind of the amortized cost to charge without going out of business, that's this quantity, the maximum quantity. If we and the goal is to have that as small as possible to be competitive with other garages or with other flat rate IT services. Good. So now let's analyze the binary counter again, but now we consider a different data type. So it's still the underlying is the binary counter, but the difference is now our data type supports both increment and decrement, right? How does that affect the amortized cost of the binary counter? If we now have a binary counter supporting both increment and decrement. And remember our definition of amortized cost. The amortized cost is the total cost of a sequence divided by the length of the sequence. That's the definition of amortized cost. More precisely, the total cost of any n-element sequence. And previously we had a n-element sequence of increments only. And there's only one n-element sequence of increments only, and that's the sequence Inc, 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 Inc. But now we have any n-element sequence comprised of both increments and decrements, and there are many more possible such sequences, right? So which sequence do we mean when we speak about amortized cost? And to clarify that, we mean the worst case sequence. So here's some example sequence. Repeatedly incrementing, that's the sequence we analyzed before when our binary counter was only supporting increments. But now our new binary counter supports both increment and decrement, which means that now also this is a possible sequence of operations. First, increment all the time up, and then going down, back down by repeatedly decrementing. Again, this is just one example sequence of operation. Another example sequence is repeatedly increment, decrement, repeatedly increment, decrement, and so on. That's also an n-element sequence of operation. So there are many such sequences of operations. And which do we mean here? In the definition of amortized cost, we mean the worst such sequence. So that's kind of a subtle point. When we talk about amortized cost, there's still kind of a worst case underlying the analysis. But now the worst case is about the worst case of the total cost of a sequence of operations, and then amortize over that is divided by n. And so previously we analyzed the worst case cost of only increment amortized, and we saw that this is constant. This is 2. But now our new binary counter supports increment and decrement, and here it turns out that here the amortized cost is larger. It is as bad as the worst case cost, namely it is logarithmic. So in the worst case, remember, almost all bits can flip, and the binary counter with value n has log n bits. That means in the worst case, one increment can have almost all bit flip. And in the amortized case, it turns out that this is the same. Maybe imagine, for example, a sequence of operations that first count up to 1, 1, 1, 1, 1, 1, 1, and then increment once again, where all the bits flip. So that new increment has logarithmic cost, logarithmically many bits flip, and then decrement. So after the increment, all bits flip, become 0, and decrement means all the bits flip back, and then increment again, all the bits flips again. So that means after the initial counting up to that bad value, then every single alternating increment, decrement flips all bits, and that's going to dominate asymptotically the amortized cost. So having both operations, increment and bad decrement, results in amortized cost as bad as the worst case cost of one single increment. So the message to take away from here is amortized cost can and will depend subtly and sensitively on which operations are supported by the data type we're considering. We only support increment, then it's constant amortized cost. If we support both increment and decrement, then it is logarithmic as bad as one worst case increment only. So now let's return to the case where we omit the decrement operation, but instead we generalize the increment operation. Increment operation means adding 1. 1 being a binary power of 2, namely 2 to the 0. So that's increment. And our generalization that we consider now is repeatedly not only incrementing, repeatedly not only adding 1, but repeatedly adding arbitrary integral powers of 2. So maybe adding 2, then adding 4, adding 8, 16, then 2 again. So any sequence of operations that adds a binary power of 2. Let's analyze that case of our generalized binary counter. No decrement, no subtract, increment and generalized increment, namely adding binary powers of 2. That's what we want to analyze here. And let's start with an example. Let's suppose the current value of the counter is this number, and I've emphasized some bits of digits in red. And now we add this binary power of 2, not 1, but here we add this number. And you see, this is the lower bits are not affected, right? All the bits that are 0 in the increment won't affect the bits in the counter value. So basically, this is the same as incrementing a counter that only starts here. We've analyzed the amortized cost for that, and it turns out that this analysis generalizes. So we observe that when adding a binary power of 2 to a natural number in binary, the number of bits that flip plus the difference in the number of ones, remember that was our bank account policy before, is still constant, is still equal to 2, regardless of what is the previous counter value and regardless which power of 2 we're adding. Always 2-bit. So that means our previous policy for maintaining a bank counter balance by maintaining the number of digits 1, the counter value, is still the same and still applicable to this generalized setting, which means that with the same bank account policy, with the same potential function, repeatedly adding binary powers of 2 still has amortized cost 2, constant amortized cost, whereas if we allow for decrement as well, then suddenly the amortized cost jumps to log n. So please keep this in mind, because this is something that we're going to recall and reuse later when we analyze Fibonacci heaps. So message to take away here: generalized binary counter that allows for addition of binary powers of 2 still has amortized cost that is constant, that is at most 2. So here's the kind of problem. We have a repeated sequence of additions of various powers of 2, different powers or same powers. And what we just established is that repeatedly adding powers of 2 incurs a total of 2n bit flips, and therefore still has amortized cost 2. And right, to recall the similarities and differences between amortized and average case, recall that in average case, we invoke the operation once, starting with a typical initial value, right? So starting with a typical value for the binary counter and incrementing it once, whereas in amortized analysis, we start with an initial value of 0, and we repeatedly increment, or we repeatedly add something. So that's an important point about amortized analysis, is that operations are invoked repeatedly sequence of increments and decrements, repeated sequence of increments and other adding binary powers of 2. That's what amounts to amortized analysis, same as the garage that repeatedly repairs cars, not just one car, but mathematically there's big similarities. Imagine having to repair one car, but it's an average car, as opposed to having to repair a sequence of cars um, um, and then amortizing the cost of the sequence. Here's an overview of the previous ways of analyzing: worst case analysis versus average case versus amortized analysis. So in amortized analysis, we fix a data structure, for example, binary counter, or later we're going to fix Fibonacci heap data structure. Data structure together with algorithms for the operations supported by that data structure. So for example, the binary counter, we first supported only increment operation. Later we analyzed that again with both increment and decrement operation. And then we analyze it again with increment and adding other powers of 2. So same data structure, but 3 different data types because they would support different operations. And we consider the analysis and the algorithm supporting these operations. And then we considered any sequence of user calls to these operations. Kind of the user being the adversary, creating a worst case sequence. And for example, in the binary counter, worst case sequence was first repeatedly increment to arrive at the counter value that has many ones, and then repeatedly increment, incurring a lot of carries, decrement, reverting all the carries, increment, same carries again, decrement, reverting all the carries, and so on. That was the worst case sequence for the binary counter with operations increment and decrement. And in general, we consider any sequence of n user adversary calls to these operations. And then we would calculate the total cost of that entire sequence in the worst case of a worst such sequence, and then amortize that total cost by dividing it by n. So that's one way of looking at amortized cost. Another way of looking at amortized cost is kind of we want to offer a flat rate service, a fixed cost service by means of maintaining a bank account balance that allows us to make savings when there's cheap operations, when there's cheap cars to be repaired, and then use that accumulated bank account balance to compensate for the rare case when there's a bad car arriving or when there's a lot of bit flips arising. That's the other way of looking at amortized analysis. And the goal is to conceive such a bank account balance, or more precisely, could conceive a policy for such bank account balances. And our traditional worst case analysis, one would consider the worst case cost of all possible inputs of length n. And an average case would consider the sum of all costs over all initial values of length n, and then divide by the number of such initial values, how many possible values can occur. And expected case analysis is something we discuss later when we talk about randomized algorithms. But here in the amortized cost, we would consider a sequence of operations. So in the end of the day, there's always some averaging occurring here, but there are subtle differences in when and how the averaging occurs. And now let's apply that to a new data structure for priority queue. Remember, what is a priority queue? A priority queue is something that allows for inserting elements and for extracting the least element. So this is kind of a weak form of sorting, where we can only access the least element, not other elements. And one way of realizing such a priority queue was AVL trees. But remember that AVL trees would not allow support for merging in logarithmic cost. So that's what led us to consider binomial heaps. And binomial heap data structure is a collection of binomial trees of different degrees. So to remind you, here's the picture of a binomial tree of order k, which is a collection of all binomial trees of order less than k, ranging from orders from 0 up to k minus 1. And here's an inductive definition. Binomial tree, let me call it a strict binomial tree of order k, is a root together with k children where the k children are by induction binomial trees of orders 0, 1, and so on up to k minus 1. So these are the binomial tree, and now we want to relax that condition. So binomial heap was a collection of binomial trees. Now we consider a Fibonacci heap, which is a collection of relaxed binomial trees. So what is a relaxed binomial tree? A relaxed binomial tree, as opposed to a strict one, is again a root with children, but the children are in turn relaxed binomial trees of different orders. So that means that these subtrees are replaced in turn inductively by relaxed binomial trees. And the operation supported by binomial tree is merging two binomial trees of same order. Same for merging two relaxed binomial trees of same order. But relaxed binomial tree also supports the operation of pruning, cutting off one subtree. But this operation can be applied only once. That's a subtle but important point. So whenever we prune some subtree from a binomial tree, then it becomes a relaxed binomial tree, and pruning a second time from a relaxed binomial tree is prohibited. So that's important to keep in mind. And algorithmically, we place a mark on the root to indicate whether a subtree has been pruned, whether it has turned from a binomial tree into a relaxed binomial tree. That's where we use a mark. Remember, we already used marks for AVL trees for balance indicators, and now this is balance indicators are 0, plus, and minus. And here we have a similar indicator, namely a mark, whether it has already been pruned or not. So pruning is only permitted from a parent which has not yet been marked, and once we prune from such an unmarked parent, we add a mark to that parent to reflect that it has been pruned and cannot be pruned a second time. So here you see that. If we prune something from this binomial subtree, yeah, this is to be applied recursively. So if we prune something from here, then we put a mark here. And if we prune something here, then we put a mark here to the root, right? So here, this tree gets pruned, and therefore we put a mark here. So that's kind of the definition of a relaxed binomial tree. And now remember our analysis of the number of nodes of a strict binomial tree. A strict binomial tree of order k had precisely 2 to the k nodes. An AVL tree of degree k had at least Fibonacci k plus 3 nodes. So this is a Fibonacci number defined recursively. And let's now recall that there's a Binet's formula that describes the asymptotic growth of a Fibonacci number in terms of the, namely exponentially, with base being the golden mean. So that means Fibonacci numbers grow exponentially, and therefore also AVL trees grow exponentially in the degree, or put differently, conversely, the degree of an AVL tree is logarithmic in the number of nodes of such a degree, and we want the same for relaxed binomial trees. We want to prove that also relaxed binomial trees have a number of nodes that is at least exponential in the order, and then conclude that the order in turn is at most logarithmic in the number of nodes of the tree, relaxed binomial tree. And to that end, we adopt our analysis of AVL trees with Fibonacci numbers. Namely, we prove by strong induction that the number of nodes in a relaxed binomial tree of order k is at least 1 for the root, plus, here comes the induction hypothesis, F1 for the least relaxed binomial tree, F2 for the next, F4, 3, and so on up to Fk for the bk minus second, right? So in the worst case, the bk minus 1 has been pruned off. So that means the worst case, the relaxed binomial tree, of order k with the least number of nodes is the one where the largest subtree has been pruned, the subtree with index k minus 1. So that means in the induction step that sum only ranges up to bk minus 2. And the induction claim is that the number of nodes in a relaxed binomial tree of order k is at least fk plus 2. That's our induction claim. And by induction hypothesis, therefore, the number of nodes of this is at least fk minus 2 plus 2, and that explains for the fk here. And the least number of nodes of bk minus 3 relaxed is bk minus 3 plus 2, and that's fk minus 1. So that means by induction we can conclude that the number of nodes of a relaxed binomial tree of order k is at least this sum. And now comes a purely mathematical claim that says this sum is equal to the fk plus second Fibonacci number. And I recommend you prove that by induction. So that's actually a different way of introducing Fibonacci numbers. Usually Fibonacci numbers are introduced by saying add the two previous Fibonacci numbers to get the next one. But an equivalent, different way of introducing Fibonacci numbers saying add all previous Fibonacci numbers except for fk plus 1. And the result will be fk plus 2. And that's something I recommend you prove by induction purely mathematically. And then indeed we can conclude that this number of nodes of a relaxed binomial tree order k is at least, according to Binet, phi to the k plus 2. But we're only interested in asymptotic growth, so we can drop the constant factor and see that this is still exponential, and therefore conversely, the order is at most logarithmic in the number of nodes, even in a relaxed binomial tree. So that concludes our analysis of relaxed binomial tree, and continuing our analysis of Fibonacci heaps. Fibonacci heaps being a collection of relaxed binomial trees, a generalization of the binomial heap data structure we talked about before. So let's conclude and record that a relaxed binomial tree, a single relaxed binomial tree of order of n nodes, has order which is at most logarithmic in the number of nodes as a consequence of our analysis that the number of nodes is at least exponential in the order, and therefore conversely the order is at most logarithmic in the number of nodes. And now we can start talking about Fibonacci heaps. Fibonacci heaps being collection of relaxed binomial trees. More precisely, a Fibonacci heap is a list of heap-ordered relaxed binomial trees with a pointer to the minimum. Now recall what heap order means. It means that the value in the node is smaller than the value in all its children. So that's something subtly different from a search tree, where the values in the left subtree are smaller than those in the right subtree. So here it's not left, right. Here it's up, down. The values on top must be smaller than the values on the bottom. So that means if we have a list of heap-ordered such trees, then the minimum node is contained in some root, and which root, that's where we maintain a pointer to that root with the least number, with the least entry. And let us use T to denote the number of relaxed binomial trees currently in the Fibonacci heap. That's something that is varying over the evolution of that data structure. And the operations supported by Fibonacci heap are exactly the operations of a priority queue. That's one way of implementing a priority queue. Binomial heap being another way. And here you see the operations together with their amortized cost. And it turns out that almost every operation has constant amortized cost. Only the extract min key operation, that's one of the operations of a priority queue, has logarithmic amortized cost. Decrease key has constant amortized cost. Merge has constant amortized cost. Insert has constant amortized cost. And create one element Fibonacci heap has constant amortized cost. So this is the improvement of binomial heaps. Almost all operations have constant amortized cost, but caveat, the worst case cost of these operations can be much larger. But when we apply that data structure repeatedly, then recall that's the amortized cost that matters, not the worst case cost. So that being said, let's now stop for today and discuss how to implement these operations and analyze this operation next time. So that's all for today. Thank you very much for your attention. And next time we'll resume with the algorithms for these operations and the amortized analysis of these operations using our bank account analogy. Actually, in this case, we're going to use two bank accounts, but that's the cliffhanger for now. Thanks and see you next time.